We will now continue with our study of electric fields by looking at electric field produced by extended charged objects. Now, what is the difference between this and what we did in the previous class? In the previous class, we talked about electric field produced by point objects. For example, you have the charged object here, which is a point charge, and we obtain the electric field E at a distance r as kq over r squared. Now, this is the equation for electric field at a point, distance r from a charge q, a point charge q. All right, this time the electric charges are not point charges but distributed over an extended object. Like what I am holding is an extended object. It is not a point charge. All right, we will be considering charges that are carried by extended objects. All right. So far, we discussed electric field due to point charges. Gauss's law will help us study electric fields due to extended charged objects. We will be discussing this Gauss's law later in the lesson or in the second part of this lesson. And then in the next lesson, we will be using Gauss's law to obtain electric field due to extended charged objects. But now we will use the formal calculations to find such fields. In order to study electric field due to extended charged objects, we will define some terms first. All right, what are the terms? First term that we need to understand is what is linear charge density. Suppose I have an object, a long object like this, and this carries an amount of charge q. What is the linear charge density? In other words, what is the amount of charge per unit length? That is linear charge density. So this is the charge per unit length of a charged object, and it is measured in coulombs per meter. If Q is the total charge that is on an object of length L, then lambda, we will represent linear charge density using the Greek letter lambda. The lambda will be equal to charge per unit length, Q over L. And what will be the unit for measuring charge per unit length? It will be coulombs per meter. The second quantity that we will discuss is charge per unit area, surface charge density. Now, suppose I have an extended charged object like this. Now, this surface carries a charge Q, which has an area A. Then, the amount of charge per unit area is called the surface charge density. So, surface charge density is the charge per unit area, and you measure it in coulombs per meter squared. If Q is the total charge on an area A, then the surface charge density represented by sigma. We will use that very often as we move on. Surface charge density is represented by sigma equal to Q over A. Now tell me, if I have this basketball, I keep this basketball always with me. Now, if there is a total amount of charge Q distributed over this surface, anybody tell me what is the surface area of a sphere? The surface area of a sphere is 4 pi r squared. So, if I know the total charge on this surface, and if you divide that total charge by the surface area, I get the surface charge density sigma. And that is something that we will be using as we move on. And the third quantity we will be using is volume charge density, represented by rho. Well, that is simple now to understand. In other words, this is the charge per unit volume. Now tell me, if I have now a solid object and it is charged, that means the whole of the object, inside and out. Now, what is the volume of a sphere? The volume of a sphere is 4/3 pi r cubed. Now, if this contains a total charge Q, then the volume charge density rho will be Q divided by the volume of the sphere, which is 4/3 pi r cubed. So, what is the unit for measuring rho, the volume charge density? It is coulombs per meter cube. If Q is the total charge on the object and V is its volume, then rho equal to Q over V. Most often used quantity is the surface charge density. But in our first example, we are going to use the linear charge density. Alright, let's talk about it. E, what does E stands for? The intensity of the electric field. Intensity of the electric field on the axis of a finite line charge. This is a finite line charge. You see, if I give some excess charge to this, how do I find the electric field produced by this, say, at a point on its axis, somewhere here? We cannot use the Coulomb's law equation that we used. We've got to modify that considerably. So, electric field on the axis of a finite charge. Now, here I have a line charge. Consider a long charged object of length L. This is the length L, and the linear charge density lambda. You understand what that is? With one end at the origin. So this end is at the origin. The length of the long charged object is L, and lambda is the surface, is the linear charge density. Tell me, if lambda is the linear charge density and L is the length, what is the total charge on this object? It will be L times lambda. Well, we need to find the electric field due to the charge on this at a point on the axis of this. We want to find the electric field at P here, a distance x0 from the origin. So the distance of point P from the origin is x0. Alright, so what does x0 stands for? The distance of the point P where we want to find the electric field. In order to do that, we are going to use the method of calculus, because this is an extended charged object. What we will do is we will take a small section of length dx. That will then act as a point charge, and then we can use the equation we derived already. So we take a small segment of length dx. This is the small segment of length dx at a distance x from the origin. So that is the distance x. Now, so that for all practical purposes it can be considered to be a point charge, and we can now use the point charge equation. We can now find the electric field at P due to this point charge. What is the equation for electric field at a point due to a point charge? It is kq over r squared. Well, tell me, what is the charge on this small segment? The linear charge density is lambda. In other words, charge per unit length. Therefore, what is the charge carried by a length dx? It will be L dx. The charge carried by this will be L dx. And what is the distance of this from P? The distance is x0 minus x. Is that right? Let's write that down. The charge on the small segment of length dx is lambda times dx. You see, lambda is charge per unit length. Multiply that by the length of the segment, you get lambda dx is the amount of charge on that segment. Alright. The field dE at P due to the charge on dx will be k q divided by r squared, where q equal to lambda dx, and the distance r is what? The distance of this from P will be this x0 minus x. So we have dE equal to kq over r squared. That will be k lambda dx. That is the charge on this. And the distance is x0 minus x, and so you square it. This is the electric field at P due to this small segment of length dx. Alright? And this is dE, which will be directed away. The field at E, the total field E at P can now be obtained due to the entire object can be obtained by integrating this dE. You see, this whole object can be divided into many such small segments. The total field at E is the sum of the fields due to all such segments. Isn't that we call in calculus integration? So, in order to obtain the field E at P due to the entire extended object, what all we need to do is integrate this dE from x equal to 0. Look at this. The position of this element can change from this end, x equal to 0, to x equal to L. This segment can be anywhere from x equal to 0 to x equal to L. So E equal to integral 0 to L k lambda dx all over x0 minus x all squared. Alright, and now k lambda is a constant that can come out. Let's do this integration. K lambda is a constant that comes out. Integral 1 over x0 minus x all squared dx. Can you integrate this on your own? Well, you can do this by using a little substitution. And that will give you, I'm going to give you the result. I'm going to leave you to do the integration on your own. Integral of 1 over x0 minus x squared is actually 1 over x0 minus x. And the lower limit is 0, the upper limit is L. If anybody wants explanation on how it is integrated, write to me. But I would expect most of you to know this. You see, I will give you a clue. The clue is this. Integral of 1 over x squared dx. You know that it is negative 1 over x. And now, if you notice that negative sign, the negative x squared will make that positive. So integral of this quantity will be 1 over x0 minus x with a positive sign. x0 is a constant. Alright, and now we replace x by L, the upper limit, minus replace x by the lower limit 0. Is that right? So that will be k lambda times, using the upper limit, this becomes 1 over x0 minus L. This is the upper limit, minus, put x equal to 0 for the lower limit. What does that become? That will be k lambda times 1 over x0 minus L, and this will be now 1 over x0, and I take x0 times x0 minus L as the common denominator. You see that? This is just x0. If you now take x0 times x0 minus L as the common denominator, the numerator will be x0 minus x0 minus L. And what does that become? x0 minus x0 will cancel. So the numerator will be positive L over x0 times x0 minus L. And now we can bring in the k lambda L right up there. You can see that would be k times lambda L over x0 times x0 minus L. Why did I color lambda L? Because lambda is charge per unit length. If you multiply that with the length L, that is a measure of the total charge on the extended charged object. So this will be kq over x0 times x0 minus L. This is the expression for electric field at a point on the axis of an extended charged object like this. Now, let's do some approximations. When P is very far, now if this is the charged object and you take a point very far, say if I'm standing at Port Charlotte, take a point in Fort Myers, then you know that x0 minus L will be approximately x0. Then compared with that distance, the length of this object will be very small. So when the distance is very large, this x0 minus L can be approximated to be x0. Then what will this equation become? It will become E equal to kq over x0 squared. In other words, you can see when the distance is very large, this object will behave like a point charge. Isn't this the equation for the field due to a point charge? Yes. Okay. A point very far from the object behaves like a point charge. And that is true for any extended object. When you take the points very far from the object, the extended object can be considered to be a point object. I think you can understand that point. Let's do an example. A uniform line charge of charge density lambda equal to 3.5 nanocoulomb per meter extends from x equal to 0 to x equal to 5 meter. What is the total charge on it? Find the electric field at x equal to 6 meter, x equal to 9 meter, and x equal to 250 meter. Alright, we got lambda equal to 3.5 nanocoulomb per meter and the length equal to 5 meter. Therefore, Q, the total charge on it, is L times lambda, which is 5 meter times 3.5 nanocoulomb per meter, and that is 17.5 nanocoulomb is the total charge on it. Well, now we need to find the electric field at x equal to 6 meter. Tell me, to find the electric field at x equal to 6 meter, do we use the actual formula or the approximate formula? Well, our x0 equal to 6 meter. Well, we need to use the exact formula. E equal to kq over x0 times x0 minus L. Now we know k, we now know q, the amount of charge on it. We know our x0, we know our L. Replace all those values. That will give you the field as 26.25 Newton per Coulomb. Alright, in the next case, we need to find the field at x equal to 9 meter. Now, can we use the approximate formula there? No, 9 meter is not too far from a charge of length, how much? 5 meter. The length of the charged object is 5 meter. So 9 meters from one end is not very far. We still need to use that exact formula. So to find the field at x equal to 9 meter, not 6, it has to be 9 meter. We use x0 equal to 9. So the same formula, the only difference is x0 now will become 9. There you are. So replace your k and your q. You know we calculated the q. x0 is 9 and that now equal to 4.4 nanocoulomb per meter, Newton per Coulomb, the electric field. How about D? Find the electric field at a distance 250 meter. Well, that's quite considerable. That means we can use the approximate formula. What is the approximate formula? X equal to 250 is very large compared to L equal to 5. So we use the approximate formula E equal to kq over x0 squared. Well, we know all these values. We know k, we know q, we know x0, which is 250. And using those values, we get the electric field as 0.0025 Newton per Coulomb. Okay, let's now look at another type of extended charged object. We now need to find the field on the axis of a ring charge. What is a ring charge? The charged object is in the form of a ring, and if you take the axis of this, where is the axis? Now, this is the axis where I'm holding my pointer. This is the ring charge and this is its axis. Can you see that? We need to find the electric field at a point on the axis of a charged ring. Alright, consider a ring of radius A. Here is a ring of radius A that carries an amount of charge Q, and its center is at the origin. Now, the center is the origin, the radius of the ring is A, and this is the axis of the ring. You see, my axis is tilted because I placed the ring a little tilted. But remember, this axis is at right angles to the plane of the ring. Alright? We take a point P on the axis of the ring. We need to find the electric field at that point. Now, you need to listen carefully. I'm going to go a little fast with this. Now, point P is at a distance x from the origin. The origin is at the center of the ring. What we do is, we start by taking a small charge, a small segment dq. The point P is on the x-axis at a distance x from the origin. In order to find the field at P due to the charge on the entire ring, we take a small element of the ring which has a charge dq. You see? We take a small element of the ring that carries a small charge dq. and we find the electric field at P due to that dq. Now, the charge dq is at a distance r from P. Can you calculate that distance r? This distance r is the hypotenuse of this right triangle, where this distance is x and this distance is a. Therefore, this r squared equal to a squared plus x squared. So the square of the distance from dq to P is r squared equal to a squared plus x squared. Therefore, the field dE at P due to this charge dq will be, what's the equation? Will be k dq over r squared. That's right. K dq over r squared, and that will be k dq over r squared is a squared plus x squared. Now tell me, what is the direction of this electric field? This is a positive charge. The ring carries a positive charge. That means the electric field will be directed away from it. That will be the direction of the electric field, and that is dE. Well, this field dE makes an angle theta with the x-axis. You see that? Now, we need to break this into x and y components in order to study that. So we need that angle. So let's say dE makes an angle theta with the x-axis. Okay? dE has a component dE cos theta along the x-axis and dE sine theta at right angles to the x-axis. Is that right? Now you know how to break a vector into its x and y components. So this dE has a component dE cos theta, well, dE cos theta in the x direction, and dE sine theta, it is the y component. Now, an element dq on the opposite end, if you now take an element dq exactly opposite to there, you will get a similar dE that has the same components dE cos theta and dE sine theta. Can you understand that? If you take a similar element of charge dq, it will produce an electric field the same amount but directed that way at an angle theta with the positive x-axis. If this is a negative angle, that will be a positive angle. And this dE will have a dEx, the x component, dE cos theta, and a y component, dE sine theta. And if you now notice the symmetry of the ring, one very interesting thing happens. All the components at right angles to the x-axis. You see, you can now construct many such dEs by taking elements all over the ring. For every element on one side of the ring, there is a similar element on the other side. That means you can construct these all around the points, which will have x components all directed in the x direction and the y components each opposing each other. What that means is all these y components will cancel and all the x components will add up. So all the components at right angles to the x-axis. You see, for dq on either side here, these two will cancel. If you take another pairs of dq anywhere, again, those components will cancel and the x components will add up. Only dEx will survive the components along the x-axis. So we need only look at the x component, all the y components will cancel. And that dE equal to k dq over a squared plus x squared, and its x component will be therefore dE cos theta. So the x component is dE cos theta, where dE is this quantity, and we now work with this. Now, what all now we need to do is we need to find that the value of the cos theta. Can you find the value of cos theta? If this angle is theta, then the angle opposite to that is this is also theta. What is cos theta? Cos theta is adjacent side divided by hypotenuse. Adjacent side is x. Hypotenuse is square root of r squared, which is square root of a squared plus x squared. So I can now write, I'm going to write cos theta as x over square root of a squared plus x squared. I hope you understand that. R squared is a squared plus x squared. Therefore, r equal to square root of a squared plus x squared. And cos theta is x over r, which is x over square root of a squared plus x squared. Alright? Now that will be, let's combine this together. That will be kx times, or kx divided by a squared plus x squared to the power of 3 over 2 dq. I took that dq and put it there and combined all the remaining together. Kx divided by a squared plus x squared times square root a squared plus x squared. I'm sure you know that is written as a squared plus x squared to the power of 3 over 2. And this is the x component of the electric field due to one small element of charge dq. And in order to find the total field at P, what all we need to do is integrate that from Q equal to 0 to the total Q. The total field Ex at P is integral of this quantity, and if you notice, the kx over a squared plus x squared to the power of 3 over 2 is a constant, because x is the distance of the point from the center of the ring. That doesn't change. And a is the radius of the ring. That doesn't change. So none of these will change. And so we can take that out, and that now become kx over a squared plus x squared to the power of 3 over 2 integral dq. What is integral dq? Integral dq is the total charge q on the ring. So that gets us the final equation for the electric field at this point as kqx over a squared plus x squared to the power of 3 over 2. So you must remember that equation. The electric field at a point on the axis of a ring charge is kqx. Q is the total charge on the ring. X is the distance of the point from the center of the ring, and A is the radius of the ring. Kqx over a squared plus x squared to the power of 3 over 2. When x is very large compared to A, what can we do? When x is very large compared to A, you can take a squared plus x squared is approximately equal to x squared. And x squared to the power of 3 over 2 will be x cubed. And x divided by x cubed will leave an x squared on the denominator. It will come to Ex equal to kqx over x cubed, because this quantity will become x cubed. And that will be kq divided by x squared, the same old formula that we derived earlier. In other words, when you take a point that is very far from the ring, the charge carried by the ring can be considered to be a point charge. That is what it means. Let's do an example. 2.75 microcoulomb is uniformly distributed on a ring of radius 8.5 centimeter. Q equal to 2.75 microcoulomb. Find the electric field on the axis at 1.2 centimeter from the center, 3.6 centimeter from the center, 4 meter from the center of the ring. Well, we know the radius is given, which is 8.5 centimeter, 0.085 meter. The charge carried by the ring is 2.75 microcoulomb. And in A, x equal to 0.012 meter. Well, we will use the exact formula for that. E equal to kqx over a squared plus x squared to the power of 3 over 2. Alright? Just replace all the values. K, Q in coulombs times x, a squared plus x squared to the power of 3 over 2, and use this on your calculator and see whether you get that value. 4.7 times 10 to the 5 Newton per coulomb. Alright, and for B part, the only difference is x will now become 3.6 centimeter or 0.036 meter. That's the only difference there for B part. For B part, x equal to 0.036 meter. So everything else remains the same. We simply replace our x by 0.036, and that gives you the electric field 1.13 times 10 to the 5 Newton per coulomb. How about C? The radius of the ring is 8.5 centimeter. We want to find the electric field at a distance 4 meter. That 4 meter is fairly far compared with the radius of the ring. We can use the approximate formula there. Since x equal to 4 meter is very large compared to A equal to 0.085 meter, we can use the approximation. What is the approximation? The approximation is the point charge formula, E equal to kq over x squared. Well, you know the value of q, you know the value of x, we know k, so using that we get the equation, the value of electric field, 1.55 times 10 to the 3 Newton per coulomb. Okay, let's look at another situation. Field on the axis of a uniformly charged disk. There is the disk. You need to find the field on the axis. This is the axis of the disk. You need to find the electric field at a point on the axis of a uniformly charged disk. And you know what we're going to do? We're going to divide this disk into rings, because we know the electric field on the axis of a ring charge we just derived. So we're going to divide this disk into hundreds of thousands of rings. Find the electric field at the point due to each ring and add them all together. In other words, we use calculus, integration. Okay, let's do that. I'm going to run down on it a little too fast, and try if you can follow these steps. Consider a disk of radius r and charge per unit area sigma. Here is the disk. The radius of that disk is r and the charge per unit area is sigma. Consider a ring of radius r. Look at this ring here. The radius of this ring is small r and its width is dr. This width is dr. Alright, P is a point distance x from the center. This is the distance x. We need to find the electric field at P due to this entire disk. You can see in my diagram I have kept the disk flat like this, and the point P is on the axis here. And you can see I have cut one ring. The ring has a radius r and the width of the ring is dr. Can you tell me what the electric charge on that ring is? To do that, you need to find the area of the ring. Can you tell me what the area of this ring is? If you take the circle, the inner circle of the radius r, the circumference is 2 pi r, and if you multiply that circumference by dr, it will give me that area of that ring. I hope you understand what that area I'm talking about. I'm talking about this area. You see that? That area I'm shading in red. That's the area I want. Now, what is that area equal to? That area equal to this circumference, this length, the 2 pi r multiplied by dr. So the area of the ring is 2 pi r dr. And if you multiply this area with sigma, sigma is the charge per unit area, that will give me the amount of charge on that ring. The charge on the ring is this area multiplied by sigma, the charge per unit area. And now, the field at P due to this charge, we're going to import the formula we derived in the previous case, is dE equal to kqx over r squared plus x squared to the power of 3 over 2. This is the formula for the field at P due to a ring charge. And this q we are going to replace by 2 pi r dr sigma, or I will bring this sigma over to here. I will call it 2 pi r sigma dr. So I'm going to replace that q by 2 pi r dr sigma. Alright, let's do that in the next slide. This q will be now replaced by this quantity. So dE, the electric field at P due to this ring charge, is k times 2 pi r sigma drx over r squared plus x squared to the power of 3 over 2. And you can see x is a constant. But what will change is now this r, because the ring can be anywhere on the disk. This r can change from 0 to big R. Big R is the radius of the disk. Alright, you can now see I have taken out all the constant factors. 2 pi k sigma x are all constants. X is not a variable here. X is a constant. It's the distance of the point P from the center, times r over r squared plus x squared to the power of 3 over 2 dr. This is the variable term. Now for the total field at P, we integrate this quantity from, you see, this ring that we taken can be taken anywhere on the disk. From this r equal to 0 to this r equal to big R. So you integrate this quantity for r equal to 0 to r equal to big R, and it becomes the electric field at P is 2 pi k sigma x integral 0 to r r over r squared plus x squared to the power 3 over 2 dr. And that is, I brought this 2 inside for convenience because I'm going to use a substitution to do that integration. Look at the substitution. Substitute r squared plus x squared equal to u. And if you take the differential now, remember x is a constant. 2r dr equal to du. So when the denominator r squared plus x squared is u, the numerator 2r dr will be du. So this, now use this to change the limits. We have r squared plus x squared equal to u. When this r equal to 0, then u equal to x squared. And when r equal to big R, then u will be x squared plus r squared. So when you make a substitution, you also need to take care of the limits. What does the integral now become? It will be pi k sigma x, integral 0 becomes x squared and r becomes x squared plus r squared. Integral x squared to x squared plus r squared 1 over u to the power of 3 over 2 du. See, this is our u, and 2r dr is the du. And you know how to integrate this. That will be pi k sigma x, integral x squared to x squared plus r squared, u to the power of negative 3 over 2 du. And the integral of that will be u to the power of negative 1/2 over negative 1/2 using the power rule for integration. And the lower limit and the upper limits for u. And simplify this. You understand this, don't you? This negative, I brought it up here, and divided by 1/2 became multiplied by 2. That's how this became negative 2 here. And u to the negative 1/2 is 1 over square root u. And now use the upper limit, square root of, using the upper limit, replace u by x squared plus r squared, minus replace u by x squared, and you have this. Okay, now I can make this negative positive by simply exchanging these terms inside. Is that right? You know a minus b is negative of b minus a. And look at the equation we produced. The electric field is given by 2 pi k sigma x, 1 over x minus 1 over r squared plus x squared. Now that is a beautiful equation. But you know, most of you I know did not follow what I did. But if you did your calculus 2 well, then you will understand all what I'm doing here. Because the integration by substitution is an interesting part in there. But if you don't understand the integration, don't worry about it. But this is important, the equation. The electric field at a point on the axis of a charged disk is 2 pi k sigma 1 minus x over square root of r squared plus x squared. But all I did is I took this x inside the square, inside the bracket. When the x is taken in, x divided by x is 1, and that x stays on the numerator. Where sigma is the surface charge density, r is the radius of the disk, and x is the distance of the point from the center of the disk. Field at a point on the axis of a uniformly charged disk is given by this formula. For very large x, it will reduce to the usual point charge form kq over x squared. And when the point is very close to the disk, that means x is very small compared to r, then you can neglect x, or this x will be 0. When x is 0, this term will go away. So when x is very small, that expression will reduce to 2 pi k sigma. I want you to remember that. The electric field very close to a charged disk is 2 pi k sigma. When x is very small compared to the radius of the ring, this becomes, you see, that part will become 0, and the electric field will be given by 2 pi k sigma. Alright, we will be using that very many times. Okay? And using k equal to, do you remember? K equal to 1 over 4 pi epsilon naught. Can you replace that k by 1 over 4 pi epsilon naught? Your electric field becomes sigma over 2 epsilon naught. I will ask you for this in the next class. The electric field at a point very close to a charged disk is sigma over 2 epsilon naught, where sigma is the charge density on the disk. Alright. You know epsilon naught has a value given by that. You know that. I've given it to you early. Let's do a small problem. A disk of radius 2.5 centimeter carries a uniform charge density. This is sigma, 3.6 microcoulomb per meter squared. Using reasonable approximations, we have an exact formula, an approximation for large distances, an approximation for small distances. Find the electric field on the axis at a distance of 0.01 centimeter, 0.04 centimeter, 5 meter, and 5 centimeter. Well, we got the radius of the disk is 2.5 centimeter, that is 0.025 meter. The surface charge density sigma is 3.6 microcoulomb per meter squared. And the formula we're going to use for the close approximation, the electric field is 2 pi k sigma. In part A, when x is very small compared to r, we use this approximate formula. So we got E equal to 2 pi k sigma. In other words, 2 pi times k is 9 times 10 to the 9. Sigma is 3.6 microcoulomb, make it to coulombs per square meter, and therefore the electric field is 2.036 times 10 to the 5 Newton per coulomb. We use the near point approximation. Tell me, how about B? What approximation we will use? Here again, compared with R, x is very small. Therefore, we can use the near point approximation. The same formula, which means the value will remain the same. You see, what that means is, if the disk is very large, it doesn't matter all over at points which are sufficiently close, the electric field will be all the same. So at this point also, E equal to 2 pi k sigma, which is the same as 2.036 times 10 to the 5. How about the electric field at 5 meter from the disk? You see, when the disk is very small, the radius is only 2.5 centimeter. It's smaller than the disk I'm holding. So 5 meter is very far. We will use the point charge approximation there. Since x is very, very large, that is 5 meter is very large compared to the radius, the charge Q is the point charge approximation. What is that? It's KQ over R squared. Q equal to A sigma, where sigma, we are only given sigma, we are not given the whole charge. on the disk. So what is the total charge on the disk? If you know sigma, then Q equal to A sigma. Do we know the area of the disk? Well, if you know the radius, then we know its area. What is the area? Pi r squared. So Q equal to A times sigma, which is pi r squared sigma. And that will be pi times the radius squared, which is sigma. And the charge carried by the disk is 7.07 times 10 to the negative 9 coulombs. And we will use the approximation for large distances, which is the point charge formula. E equal to kq over x squared. That is 9 times 10 to the 9 is k. Q is 7.07 times 10 to the negative 9, and x equal to 5, and that is 2.55 Newton per coulomb. So we used in two cases the close approximation when x is very small, and in the third case x is very large. How about D part? Find electric field at x equal to 5 centimeter. It is not too small, not too large. You need to use the exact formula there. The electric field is 2 pi k sigma times 1 minus x over square root r squared plus x squared. So we use the normal distance formula and use all the given values. 2 pi times k times sigma, 1 minus x is 5 centimeter, 0.05 meter, over r squared plus x squared. R squared is 0.025 meter. Alright, replace r by 0.025, and that will give me 2.14 times 10 to the 4 Newton per coulomb. So if you notice here, we treated three cases. We had a long object, we obtained the electric field on the axis of that. We had a ring charge, we found the expression for electric field on its axis. And finally, we found the expression for electric field at a point on the axis of a disk. Now, you don't need to particularly worry about the derivations I gave, but you need to remember how to use the formulae for calculations. Alright, now what I'm going to do is develop Gauss's law in the next section and use Gauss's law to obtain these equations, which is a little more easier than using calculus. You can do away with calculus and use Gauss's law to obtain the same equations. We will do that in a later lesson. Alright, I will get back to you with the second part of this lesson a little later. Alright, until then, take care and do all the homework and try and do some of these on your own. Alright.